Mass transfer plays an important role in our lives. Perhaps the most pertinent aspect of mass transfer to our daily lives is the concept of molecular diffusion. And we can see molecular diffusion in a variety of different scenarios. One example would be dissolving sugar in coffee, or another example would be spraying air freshener in the air. The scent naturally diffuses throughout the room. But you might be asking, what causes molecular diffusion? In general, we can think of molecular diffusion as the movement of molecules from areas of high concentration to areas of low concentration. And as you can see here, just a simple graphic, we have our green solvent and our blue solute, and in this side, the solute is highly concentrated, and then over time, it's going to spread out until the entire area is of equal concentration at all points. Overall, molecular diffusion can be effectively modeled by fixed law. We see here that we have the diffusive flux, and it's equal to the diffusion coefficient times the concentration gradient. No one likes calculus, so we're going to ignore this. Instead, today, we're going to be focusing on the diffusion coefficient. And as might be expected from experience, the diffusion coefficient, and thereby diffusion as a whole, depends on both the identity of the solute and the identity of the solvent. With this in mind, we've planned an experiment in which we're going to place blue dye in a variety of different liquids, and we're going to see how this affects the diffusion coefficient. But let's look at our experimental procedure with a little more detail.
For this experiment, we measured out 6 flasks consisting of water, vegetable oil, dish soap, acetone, isopropanol, and bleach. We chose these different liquids because of their varying physical properties. Using a pipette, 1 drop of blue dye was carefully added to each flask just above the surface in order to introduce as little momentum to the system as possible, as well as reducing the initial effects of convection. Immediately after the drops contacted the surface of each liquid, we recorded the time it took for the drops to fully diffuse through the flask. We qualitatively defined fully diffused as blue dye reaching the sides and bottom of the flask, as well as no blue streaks and general visual homogeneity. For more viscous liquids, the diffusion of the dye was extremely slow. In this case, we will cap the experiment time to 10 minutes and qualitatively compare the extent of diffusion to other liquids.
So what just happened? We saw that the dye diffused the quickest in the acetone, and we saw that the diffusion was slowest in the bleach. But is there a way to predict this result? It turns out there is. One of the most common equations used to estimate the diffusion coefficients within liquids is the Stokes-Einstein equation. From this equation, we can see that the diffusion coefficient depends both on the radius of the solute and the viscosity of the fluid. Molecular radii are difficult to find, so we cannot use this equation to directly solve for our diffusion coefficients. Instead, since the molecular radius is constant, we can determine the order on the basis of viscosity. The viscosity of various liquids plays a large role in determining the diffusion coefficient for each experimental trial. If we look at the equation, viscosity is in the denominator. As it increases, dV decreases, and vice versa. This makes sense from an intuitive standpoint. Viscosity can be considered the thickness of a material. For example, honey is much more viscous than water, so we'd expect the dye to diffuse slower. One thing to note is that the vegetable oil did not behave as expected due to a lack of solubility of dye in the vegetable oil. This equation assumes that the liquids are exhibiting ideal behavior, but as we saw in the video, the dye just sat on top of the oil and did not diffuse into it. This suggests that there is some interaction occurring between the oil and the dye that prevents the diffusion from occurring as expected. We use the values of viscosity and centipoise for our 6 liquids to calculate the diffusion coefficients. As we can see, the highest viscosity liquid was bleach. It also has the least amount of diffusion within 10 minutes, and therefore the smallest diffusion coefficient. On the other hand, acetone has the lowest viscosity of only 6, and as expected, it diffused the quickest. Repeating these calculations for the remaining liquids, we see that the predicted order of the diffusion coefficients matches our experimental observations.